we need some rules to understand how we build this up. And I'm going to give you examples for each one. But to some extent, what we're going to do is just show ourselves that these rules hold. And then we're going to use those rules of inference when we build out proof later on. Okay? Okay, so their basic rules to build arguments are called the rules of inference. How do we infer the next piece of information? And these are just building blocks. So we're going to put them together over time to build out more complex arguments, but these are the pieces we need. Okay? So there's two that have names that I care about. The rest of them you'd look up, but they're kind of weird names. And that's because they're Latin. So the first one is called modus ponens. And what that means is the mode that affirms. Okay, which means, let's see the example of the form. So this is the one that we've just seen. P implies Q. P holds, therefore Q follows. Okay, so this is what we've seen. And this is the tautology related to it that we've looked at. And what that means is we have this implication. We have affirmed that the first bit is true. And so this is the mode of what happens when the antecedent is affirmed, that P is affirmed. So an example of that is if the password is correct, then the user is allowed in. We see this all the time. And all of these things, when you think about what this looks like, all of this happens behind the scenes. And we'll go through examples. When we're programming, your computer is doing all of this logic. So if the password is correct, the user is allowed in. The password is correct, therefore the user is allowed in. Okay. It has a counterpart, and it's called modus tollens. And I'm going to give you names for other things. These are the only two that I actually care about the names, okay? And this means the mode that denies. So now we have, it's similar. We start off with this implication, just as before. P implies Q. But then we see that we have not Q. So we have a situation where implication holds, but we have that the consequent Q is negated, not Q. So an example of that here are premises. If the password is correct, then the user is allowed in, same starting point. But this time we have the mode that denies. The user is not allowed in. So that is I'm keeping the colors to match, not Q. The user is not allowed in. Therefore, the password is not correct. That's our not P. Okay, so if that second piece does not hold, the consequent does not hold, then the first piece must not be true because we're assuming this all to be true. So I think it was stated earlier. So what's another way that we can state P implies Q? Either Q holds or P can't be true. So this is another form, and this is a valid form of logic because what you can, this is another way to think about it. And the reason for that is if you see this, if these are the same, right? P implies Q is the same as Q or not P. But if I assume both of these are true, not Q tells me, well, that's false. And so the only option then is that not P is the answer. And we're not going to go through proof of all of these. I want you to have some intuition as to why that's a valid argument form. And that's where that comes from. Okay, so here's some other rules of inference. And once we get to this other rules, the name doesn't matter to me. Okay, I'm not going to say, what is the form of hypothetical syllogism? So this form is different. So this is saying if P implies Q and Q implies R, then P implies R. So what is the conclusion that you can draw from this. If it rains this weekend, then I will study discrete mathematics. If I study discrete mathematics, I will get an A. Therefore, if it rains this weekend, I will get an A. I do hope for sun. Rain isn't the only thing that will cause you to get an A. Okay, so this is another valid form of logic. Other rules of inference. P or Q, not P, therefore Q. And we know that P or Q means that we're assuming this is true. And if we assume this is true, then one of these must be true. But our other premise is not P. Well, if not P is true, that means P is false. And if P is false, then the only thing that can possibly be the case is that Q is true. And so that's how we draw the conclusion Q. Again, I'd love you to draw the conclusion for me. It will be sunny or cloudy. It is not sunny. Therefore, it will be cloudy. Exactly. If I start with the premise that P is true, then I can draw a conclusion that either P or Q is true. And this might sound really, really strange, right? So if we have P, Java is fun, then we can draw a conclusion. Name a conclusion that we can draw. You might all be right. You can all have different... So I didn't claim that my premise was necessarily true, even though I would agree with it. But if we assume my premise is true, that Java is fun, from the rule of inference addition, what could I conclude? Yeah, Java is fun or anything. So therefore Java is fun or Python is simple. But because we've assumed this to be true, then an or statement, the reason this works is essentially we're saying P is true. We assume that P is true. Then this becomes the form true or Q. But in this case, no matter what we do, because the first one is true, the whole thing is true. So it doesn't matter what we put there, which is an important piece. So Java is fun or my name is Michael, right? It can be completely anything. Java is fun or I'm going to Disney World tomorrow. Because we've assumed Java is fun, despite disagreements, we'll assume it's true. Okay, so then we have this kind of is so this is addition. We're adding on another piece. And I'll show you that there are times that we want to do that to work with other rules of inference. So it'll make sense over time. Because right now, I understand addition seems like a crazy thing. This one might seem a bit more obvious. So simplification. And this is the idea that I'm going to assume that both P and Q are true. And what do we know about and? If this is true, what can you tell me about both P and Q? This can only be true when both are true. It's okay then to conclude that P is true. It would also have been okay to conclude that Q is true. They have the same form. Okay, so let's then come up with a conclusion for this. Today is Saturday and it is the weekend. So there's our and. And so we've got P and Q. So I could draw one of two conclusions from this. Today is Saturday and it is the weekend. Unfortunately, the premise is false. But assuming that premise is true, therefore, today is Saturday. So therefore, today is Saturday. I wish it was the weekend. Which one? But unfortunately, my premise was false. Okay, so then I can also have the rule of inference around conjunction. So if I assume that P is true, and I assume that Q is true, then I can draw the conclusion that P and Q is true. And this makes sense, right? So if I say it is raining, it is cloudy, Therefore, it is raining and cloudy, right? Keeping that and. This just makes sense, and that comes from the rule of conjunction. I can also use my final rule, and that is resolution. So if I say that either P or Q is true, and not P or R is true, okay, then I can conclude that Q or R is true. So what does that look like in practice? And then I'll come back to some intuition around that. But I think it sometimes helps to put that to a concept. So it is sunny or raining. It is not sunny or cloudy. Therefore, what can I conclude? And so take a look at the form of these things. And I do color code it. So what is the conclusion I can draw? Yeah, it is rainy or, it's important, the or cloudy. Okay, and we can see why this is the case. Because essentially what we have is, it is either sunny or raining, not sunny or cloudy. The problem is, we cannot have both sunny and not sunny. And so all we can do is get back to Q or R. If we want to build up more complex arguments, we want to use what we've already learned. So we're going to build valid arguments that are a bit more complex by taking all of those rules together and using them. And so